Alright, hey everyone. Another Structure Pro video here, and we're just going to be going over Mohr's circle for plane stress in this video. So that's a pretty busy screen we got here, but we're going to work our way from the top to the bottom and just establish some of the notations. That's what we're going to start with. Then establish the transformations and link these equations we see down here with the graphical circle itself. So notation. First thing we have here is the 3D stress representation, and that has 9 components. And we're just going to be dealing with plane stress here, and so that significantly simplifies things. Thank goodness. So plane stress can be applied to a thin plate or free surface, so long as loads are not on the free surface or, in the case of this thin plate, out of plane. And basically it just makes any component with a z or a z equal to 0. Alright, so that simplifies things to only 3 components. So we basically just have 2 normal stresses and a shear stress. So we generally write that in the 2D representation there in like an xy plane, and we only have to write down 3 of the values because on the opposite side it's assumed to be the same. Next, we're going to look at how we can transform a given stress state. And what we really mean by that is look at an element in a slightly different way so that the stresses on the faces are different. And so we're going to be rotating an element by an angle theta, and that's going to change our reference, and it's going to change basically our axes. So now, instead of having sigma x and sigma y, we have sigma x prime and sigma y prime. And there are equations for doing that, which I haven't shown here, but trust me, there are. But here I've only shown the important equations, what we need right now. But essentially we're starting with the sigma x, sigma y, and tau xy, and we can get this sigma x prime, sigma y prime, tau xy prime, or more importantly, we can get what we call the principal stresses. So that's sigma max, sigma min, and then there's the principal shear, or the maximum shear really, tau max. So that's listed over here on the right. It's this special unique angle, theta p, called the principal angle, and it rotates you to a position where the shear disappears, okay? You can see no shear on the edges here. That means that we've actually maximized our normal stresses. And this is very key for a variety of reasons, but failure being one of them. So the max shear actually occurs 45 degrees rotated from that, and the value of the max shear is going to be equal to R, this equation down here at the bottom. And now the equations will start to make more sense in the context of this circle. So just written down the equations at the top, and then we're going to link them to this circle, or this graph. And the guy who developed this was a German guy with just a little too much time on his hands. One of the first things we can notice is that the sum of the normal stresses doesn't change regardless of what orientation you're in. And as a result, neither does the average. So we're going to take a leap of faith here, and we're going to plot the average along the x-axis, or what we're calling the sigma axis. Next, we're going to make the radius of the circle equal to this value r. Okay, so the value r, which equals tau max. And this makes sense because this y-axis, or what we're calling the tau axis, it has maximum and minimum values of r at tau max. Alright, so let's look at the next equation. Sigma max is equal to the average of the center of the circle plus the radius of the circle, and so too sigma min is the average minus the radius. Now we can label different points along the circle, so we'll label sigma x and tau xy, and sigma y and tau xy at the bottom left. These 2 points are linked by a line that crosses through the center of the circle, and those represents any old stress point, but in this case it's not the principal stress. And we can actually see how we got this r equation just looking at the distances and applying Pythagorean theorem between those distances of r. So pause that if you need to take a closer look. And we can also apply trigonometry to find this principal angle. And as it turns out, every angle in the Mohr circle needs to be divided by 2 when you're applying it to the actual stress transformation. So we notice in the Mohr circle, the principal stress state is 90 degrees rotated from the state of maximum shear stress. And in real life, we know that's actually 45. So just to clarify what this circle actually is, points along the circle are basically possible stress states if the element is rotated at different angles. So if we're given an arbitrary stress state, sigma xy and tau xy, we can find sigma max, sigma min, and tau max, and these will end up being important parameters for failure criteria for different materials. Okay, thanks for watching. Stay tuned for some examples, and any comments or questions just put down below.